Hi, we're Team CSC from Prospect High School. Over 10 weeks of collaboration, we created an app to demonstrate the flight path of the Artemis II mission. In the process, we added a variety of useful features to make the data easier to view. The most important data is shown in the top left of the app, such as the mission status, time elapsed, position, velocity, distance traveled, mass, and satellite connectivity.
All the data in the app is processed and housed in the SimVars C# script. Any other code file, whether it controls the position of an object or what a text box says, references the variables in this. However, the most prominent feature is actually seeing the mission path, and it can be viewed in a variety of ways.
The camera has three main modes, each related to the reference frame from which you're viewing the data. The first is a fixed point far away, showing the entire mission. The second is a zoomed-in tracking mode, which follows the spacecraft at a fixed distance and angle. The last mode is a free tracking mode. It follows the spacecraft, but you can adjust the distance and the angle you want to view it from. In this mode, on computers, the mouse can be used to turn around and the scroll button can be used to zoom in and out. On iPads, you can use touch controls for the same effect.
The time is controlled by the slider at the bottom or by a user-set speed multiplier of the normal time. If the app was displayed in real time, the simulation would have taken over 10 days. For a cleaner and less user-driven mode, we also created simulation mode. This mode mimics what it might look like for a real-time mission.
Even while you're zoomed in, you can still view the full mission path using a helpful mini-map in the bottom right. Note how the color is used to signify the different sections of the mission. This color scheme is used in the mission status label, in the main path, and the mini-map.
Color is also used for the satellites. Each satellite is plotted on the Earth with different colored dots representing each satellite. These help visualize the line of sight access from the antennas to the Orion spacecraft. The satellite connectivity also uses color to show you what satellites are available as well as what satellite is recommended. The user can choose the recommended satellite based on the highest data rate or the least amount of antenna changes. The data rate is calculated by the link budget cost formula given to us by NASA.
There are also a variety of settings available to customize your experience. You can adjust the size of the UI, which also adapts the screen or the window you're viewing it on. The data and the menu shift to the sides and transform based on how the app is used. You can toggle the velocity and the acceleration arrows on or off. The velocity is directly from the data set, and the acceleration is calculated in the change of velocity divided by the change in time. For enhanced realism, the user can also turn on realistic lighting. By default, the simulation is lit up in a way that makes all the objects easy to see, but you can turn on lighting that is more accurate to what real life would look like.
There's also a toggle for our enlarged mode. This adds unrealistic proportions to 3D models, which makes everything very easy to see and visualize. The mission path is also distorted and expanded, allowing the 3D models to be visible and not overlap each other. In order to achieve this, we used a special algorithm to loop through the data and apply some math that expands the data points around the Earth and the Moon. I first wrote out how I want to modify each data point, then create a function in our main C# file for processing the data.
Lastly, you can toggle on an overlay of the off-nominal mission path to show the difference between the two data files.
Throughout the process of creating this app, we ran into and overcame a variety of challenges. One we encountered was with our time system. The user can use the scroll bar or automatic speed controls to adjust the current time of the mission. However, when the time extended into the tens of thousands of minutes, we were attempting to add small decimal values, the real-time seconds. We began to run into issues with the rounding and with the float system within Unity.
To solve this, we switched to a new variable type, a decimal. While most types of numbers can use decimal values anyway, this variable type is specifically meant for handling large, precise numbers. With this new time system, we're able to completely control the mission time. We can control the whole mission with a slider or simulate real time. The simulation could be also sped up, slowed down, or even reversed to fit the user's needs.
Another challenge we faced was making the camera mounts. This took a lot of iteration as the camera had to be programmed to go around the spherical coordinates of the ship as moved in real time. Along with this, in the free tracking mode, rotating around the spherical poles of the ship posed major problems as it would cause erratic behavior. This was fixed through the introduction of a smoother .lerp function and using more accurate trig values.
After interviewing with NASA personnel, we also gained valuable feedback that helped us improve our project. The judges noted that the path lines displaying the motion of the moon and the Orion spacecraft were too thin and was hard to see at times. So we increased the line thickness for all the elements for enhanced visibility. With the addition of the judges' suggestions, we were able to take our app to the next level.
Colors, as we've said, is a major component of the app. Based on judge feedback, we added a new menu next to the settings that shows the color palette of all the components. Altogether, the technical suggestions allowed us to improve our application and made it so we can make the app more user-friendly.
Before showcasing our app to the community and submitting it, we had multiple mentors and advisors review our app. As with any project, diverse and unique perspectives provide stronger results. First, Mr. Larry Schroff, a former Facebook and Shopify engineer, was impressed with the design and offered insightful advice for refining the app's user interface. Additionally, after attending an astronomy night at Northwestern University, I connected with 2 qualified students studying physics and computer science, who had expertise in space science. They helped us further refine the app and conceptually understand the data.
We aim to further use our project to inspire the next generation of developers and engineers. To achieve this, we reached out to a variety of local middle and elementary schools, 2 of which accepted our offer. We first presented to a local middle school science Olympiad team, followed by a session with a class of 5th graders at a local elementary school. During these presentations, we not only showcased the features of our app and how it was made, but also discussed the Artemis II mission and its significance. Additionally, we explored emerging quantum technologies and their impact for developers all around the world. With its many accessibility and customization features, we also envision our app being helpful for the future. By changing some Artemis II specific variables and uploading a new data file, our app could easily be edited to support new missions.
There's not much we would have changed about the software and processes we used, since we had a great setup for working and collaborating efficiently. However, we still learned a lot throughout our journey of designing, developing, and testing this app. All of us gained important skills in both technical and collaborative aspects. We are incredibly grateful for this opportunity and are so excited to see what the future holds.